Thank you very much for your kind introduction, and thank you for the invitation to speak here. I'm very honored to talk to the membership of the RCI. So, like I was just introduced, I'm Jane Heffernan. I'm a York Research Chair, Tier 2 at York University, and the title of my York Research Chair is in the Multi-Scale Methodology for Evidence-Based Health Policy. So I'm really looking at developing mathematical models and computer simulation tools to address questions that are of relevance to public health policy. I'm also the director for the Center for Disease Modeling, and this isn't working. There we go. And I'll just give you a short introduction to the CDM. We originated from a MyTax group during the SARS crisis in Toronto. MyTax was a funding agency that funded mathematicians and computer scientists. And this group involves mathematicians, public health, computer scientists, immunologists, and engineers across Canada, both at universities and in public health agencies and government. We have a global collaborative network, and in particular, we have some Canada, China, Africa, India, and Brazil initiatives that include exchanges, and we're funded mostly by NSERC, CIHR, MyTax, and government contracts. So the CDM came from this group. The CDM was formed in 2007 formally at York University. Some things that some diseases that we address, or some questions in medical policy and public health policy, have to do with these things down at the bottom: antimicrobial resistance, foodborne diseases, pandemic flu, STDs, TB, Hep B and C, neglected tropical diseases, vector-borne diseases like Zika virus, respiratory pathogens like MERS-CoV, waterborne diseases, and zoonotic diseases. So we are involved in many different activities, quite a few summer schools, and that's actually how I was introduced to the MyTax group that formed the CDM, because I was a graduate student at one of the summer schools when I was doing my PhD. We have workshops and conferences, seminar series, and many other things, and a lot of these are in affiliation and collaboration with the Fields Institute. Okay, so all of the researchers and government partners and officials that are part of the CDM try to address questions in infectious disease policy that lie on this multi-scale problem. So here we have pathogen and cells in your body that are interacting. That goes up to what's happening in the individual. And then we're looking at the individual level, how individuals in the population can help spread the disease, and how susceptible they are to contracting the disease depending on their contacts in the population. And then you can see that might just be really a classroom in a school, and this might be the school, and then you can think that this might be certain workplaces, our homes, or church, or the shopping mall in the community. And then these places within the community can change their disease status over time. So you can go from susceptible to recovered. You could have some infection, and then you become susceptible again over time, depending on the length of time that you're looking at. And then you can think that this entire community is one population that's in a multi-population or meta-population. We have lots of different communities that are linked through roads or commuters, the GO train, things like that. So we try to address questions through all the different levels of infectious disease policy, where we might include, so this is a tick that helps spread Lyme disease, which we know is something that plagues Ontario right now. Here's a mosquito for West Nile virus, for example. So we're interested in looking at things where we're trying to catch ticks and mosquitoes and count them to see how prevalent a disease might be in the environment. Here is a model for looking at just what happens inside the body, where you have a pathogen. It's an HIV virion, how it infects a cell and how the cell produces new virus. So something in host modeling. Here is the diagram for the pandemic H1N1 and how it developed. So we're also interested in looking at evolution and how diseases come from zoonotic events. And then this is a diagram that I borrowed from the Biodiaspora project, which is also called Blue Dot right now. So we have some researchers in the CDM that are affiliated with this company. And this is your air traffic network. And so they're really interested in looking at what's the risk of importing infection into one city from another city. And so something that they could be interested in, well, this is the map that they used to look at the importation of infectious diseases into London when London had the Summer Olympics. Okay. So in terms of control policy, we're interested in looking at vaccination programs. So you've probably heard of vaccine hesitancy. How can we kind of get a quantitative definition of vaccine hesitancy in the population, and how can we address that? We can also just look at what happens if we introduce a new vaccine into health policy, or if we introduce a booster vaccine. That's something that's being considered across the world for pertussis currently. Here's some drug therapy. So HIV, how that helps patients bring down their viral load. You can also think that drug therapy could be included in models of influenza where you take some antiviral to lessen your symptoms, and how would that affect your transmissibility, for example. We're looking at vector-borne controls as well, like bed nets. Here's the spraying of the repellent in Winnipeg. Here's some safe sex practices. And then this is also just looking at a public health media campaign. And this was during the last pandemic. This is the region of Peel, and saying how to stop spreading germs, minimize the length of time that you're out in public places, mass gatherings. Tell staff if you have cough, fever, flu, sneeze, cold, sneeze in your sleeve, things like that. So we try to also determine the efficacy of these media campaigns as well. Okay, so that's the CDM. My lab is called the Modeling Infection and Immunity Lab at York University. It's called the MI squared. And what we're really interested in is looking at how what happens in the host shapes your susceptibility and immunity, then how that translates to transmissibility in the population, which then, if you think about if you have transmissibility, then you have the disease in the population at a certain level. And so then you have to think back down to you have to think up to the metapopulation scale, where now you have a disease that's prevalent in all of these populations that you may travel to. And then how does that affect the force of infection on me for this disease in the future, which then helps shape my susceptibility and immunity again. Okay. So you can think that you could be exposed to the chicken pox when you're a child. We could have a nice mathematical model that would describe your development of immunity over that course. And you all believe that you have lifelong immunity to chicken pox. But what if that really just meant that if your immunity waned, well, as long as chicken pox is around and you become exposed again and again and again, then you get these boosts in immunity. So effectively, your immunity is lifelong, even though maybe your immunity really does wane over time. Okay, so specific questions that we look at are, how does the immune system interact with a pathogen? How do you develop immunity? How is this related to transmission? And how does some population immunity affect epidemic size? So we look at various different infectious diseases in my lab at different scales, in-host, between-host, the population level, and in collaboration with experimentalists and government. And I'm going to talk about HIV, measles, pertussis, the flu, and social distancing today. The mathematical tools that we use involve dynamical systems, stochastic models, which has just really based on probability, computer simulations, and then some analytical tools on bifurcation and stability analysis. Okay, so here's the basic disease model for describing the transmission of disease or the propagation of disease in a population. So you can think that you have a population where you can group different people in the population into different compartments. You can see that here all the blue people are susceptible to a disease. The exposed people are people who are infected that are not yet infectious. Then they become infectious individuals, so they're the orange people. And after you're infectious, you will recover, and then we can assume that these recovered individuals can have immunity, so they're resistant to infection, but then over time they might become susceptible again. Okay. So something that we look at is, okay, what happens if we put the vaccine into this population? So we could have another vaccinated compartment. You can say that maybe all those individuals are white. And what you can see is that if we change some of these individuals into a white color, which you won't be able to see, then you can see that really what that means is that you're making the distance between susceptibles and infecteds and susceptible individuals further apart. And so you can think that the vaccine really is helping provide a barrier surrounding these susceptible individuals so that you can decrease the probability of infection. Okay. And that's what we do when we're looking at herd immunity. So we're trying to determine what is the fraction of the population that needs to have a certain vaccine in order for the entire population to be effectively immune. And so you can think for measles, that threshold is about 95%. So we need almost everyone to go out and get the vaccine because we know that the vaccine takes in 95% of the people that get it. Okay. Now that was just an SEIR model, susceptible, exposed, infectious, recovered. You can think that we could involve many, many other different compartments into the populations. People could be susceptible, exposed, infectious, or recovered. You could have recovered individuals that going down to some waning immunity, where now here, if they're re-exposed, they can be boosted back up to recovered. But if they continue their immunity to wane, then they could go back to the susceptible compartment, or if they get infected here, then they could go to exposed, but maybe they won't show symptoms. You can also have the vaccinated individuals who could also wane to W, and you can so here you can have infectious individuals that recover, or we know that for some infectious diseases, you can recover or not. You may become chronically infected, and you can go up to this chronically infected compartment. Okay. So there's so many other things. You can also put in classes for treatment in here. You can put in classes for isolation, or if you're electing to stay home to minimize your contacts. There's so many other things that we consider in the population. But one thing that we also need to consider is that really all of these compartments, what happens to an individual that's susceptible will depend on what its immune system status is. And if you have some immunity, you may become infected, but what you experience here and here might be greatly decreased because you have some immunity. Okay? So you can think that you may have a lower level of symptoms. You could still have a high enough pathogen load to be transmissible, but that could be a lot lower than if you didn't have any immunity at the beginning. And then you can think that this is also going to determine what level of immunity you have at the end. So what level of immunity you have at the beginning is going to determine what level of immunity you have after you are infected, which could be a mild infection, a stronger infection, or it could really just be a boost in your immunity and you're not really infected at all. So then you could think that all of those individuals that were in the population, we could now embed an immune system into each person. Okay. Now here's a diagram of how different cells in the immune system interact. Okay. So we have B cells, which are important for making antibodies. And we have helper T cells, which are important for activating the rest of the immune system. We have CD8 T cells that are down here, and when they're activated, they can kill infected cells in your body. lots of different things that could happen. Never mind. So this is just your adaptive immune response that's specific to a pathogen. You have lots of other components of your immune system in your body that are non-specific as well, like cytokines and interferon and macrophages and dendritic cells. But you can think that then if we want to embed an immune system into all of our individuals, and we already have a huge number or a huge model for describing the disease at the population level, then we're going to have even a more complex model if we want to put the immune system inside everybody. Okay? So then what we really have to think about is, okay, we could put in all of the biology we want, everything, just put in everything in there. But there are going to be so many unknowns that we can't measure that we're not going to have all of the parameters that we need to actually run computer experiments or mathematical experiments to see if we understand what's going on. So there's a lot of uncertainty in there. So what we really need to do is we need to, say, what are the most important components for this infectious disease? So you could think for flu, an important component is antibodies and interferon, for example. For measles, we might think that maybe the most important component for the immune system is the CD8 T cells. And we gain this type of knowledge from reading and collaborating with individuals that study these infectious diseases at both universities and that know a lot in government and public health. Okay, so that's quite complex. We need to simplify. So what we're really given is a problem where if we incorporate a lot of the biology, then the level of new knowledge that we get is very small or non-existent, because there's so much uncertainty in there that we can't actually conclude anything. If we decrease the level of biology so that we have a well-defined system where we know quite a bit of the parameter values, then what we really want to do is we want to optimize, we want to simplify the biology enough so we have the most important components in there and optimize the new knowledge from our results. We want robust results. And you can think that if you get too simple, then you're really going to have no new knowledge again. So that's the problem that we're faced with. It's not just the problem that we're trying to model. There's also that integral issues to figure out what do we need to include into our model so that we can actually say something in the end. Okay. So the first infectious disease that I'm going to look at is the human immunodeficiency virus. So what we're interested in is, well, we're really trying to understand this latent phase of infection. So you have an acute infection up to about 8 weeks. You have this long latent phase, which is up to 12 years, but longer if you're on effective drug therapies. And then this, after a while, can progress to AIDS. Okay. So this is a nice picture that you always see in presentations of HIV, or a variant of this type of picture. But there's a problem with this, is that this says that every HIV patient is about the same. They follow this trajectory. So that's deterministic, but we know everyone is different. So there's going to be some variability around this. We also know, though, that the way that the pathogen and your cells in your body interact has to do with probability. There's a probability that they interact at a certain time. So when you take the viral load or CD4 T cell count in an HIV patient, what you're really going to see are some fluctuations around what you think that this mean is. So there are going to be some fluctuations like this. Okay. So now you have some fluctuations. Well, suppose your patient is now on a new drug therapy, and you're taking their CD4 T cell count and their viral load maybe so many days apart. Well, you should expect that the measurements are not going to be the same. There's going to be variability. So what if the second measurement is higher than the first measurement? Does that mean that their drug therapy is not working? Maybe not. It could just be a natural fluctuation that you're actually seeing. So what we tried to do, this was during my PhD, was develop a mathematical model that we're trying to figure out how much biology do we need to include in a mathematical model of pathogen dynamics for HIV that can actually replicate the variability that they're measuring in the clinic in HIV patients. And then what can we say about this expected variability? Okay, so here are some actual viral load measurements from different patients, and these are individuals that are on different drug therapies. You can see that for some individuals, it's not jumping up and down that much, but you can see that for some other individuals, there are some jumps, and these are just measurements that are so many days apart, so you can think that there's going to be more variability in between these as well. Okay, so can we model this, and how much biological detail do we need to include in our model so that we can get the variability measurements that they get in the clinics? Okay, so we developed a simple mathematical model that just considered CD4 T cells, because those are the cells that are infected by HIV, which is terrible because those are the cells that activate the rest of your immune system. So you can think that if someone who has HIV, as their infection progresses, they're becoming immunocompromised or immunosuppressed because they don't have a very robust immune system to fight off other infectious diseases. Okay, so what we did is we just included the CD4 T cells and the pathogen. And then we tried to see, using our computer simulations, what's the expected variability that we would expect in a patient using our computer simulation over a very long period of time between measurements. Okay, and that's what these red numbers are. So for cell count, we obtained a measurement of 0.11 log base E CD4 T cells. Well, this is what they measure in the clinic with prolonged measurements between prolonged measurements for a patient, so a long number or a long length of time in between the two measurements for one particular patient, and then they do a cohort study to get an average. And they measure about 0.25 log base E CD4 T cells, so it's along a similar magnitude. It's not the best, but it's not terrible either. But then when we go down to the viral load, our simulation measured 0.02 log base 10 RNA copies. And in the clinic, they get a measurement of 0.2 to 0.4 log base 10 RNA copies. So this is very far off. It's not close at all. So what that said to us was, okay, just having infected cells and healthy cells and virus in our model is not going to help us replicate what's happening in an HIV patient. It's not going to help us understand this expected variability between measurements. So we have to add more of the biology. And what we did is we added CD8 T cells. Those are those cells that when activated can go out and kill infected cells in the patient. Okay? But we also included the fact that when a cell is first born into your body, it's naive. And when it's activated, it's only then that it can go out and kill infected cells. It can't while it's a naive cell. So all we did was include these two components into our model. And you can see, so now we're going to the green numbers, that for a long length of time between measurements, now we get 0.22 log base E CD4 T cells, which is very close to 0.25. And down here, we're getting 0.32 log base 10 RNA copies, which is right smack dab in the middle of this range that's reported clinically. Okay, so we thought this is great. We're replicating things that are happening in the clinic. What else can we find with our model? Well, firstly, there's a caveat here, or a warning, is that we were modeling 10 microliters of blood in a patient. And it just so happened that 10 microliters of blood is going to give you something very close to here. You can think that as you increase the amount of blood that you're modeling, the variability is going to decrease. If you decrease the level of blood that you're modeling, or the amount, then the variability is going to increase. Okay, so we just kind of stumbled upon a result where now we were able to say, okay, in order for us to determine what's happening in the clinics, we have to model 10 microliters of blood. Okay, so then what we did, so that was for a very long length of time in between measurements. So what we were then able to do was say, okay, so that's out here. What if we only have 1 day between measurements, or 2 days, or 3 days, and so on? And so that's this model here. What happens if we have 1, 2, 3 to 10 days to 20 to 30, 40 days in between measurements for patients that are on drug therapy? And that's this blue model here. Okay. So you can see that the expected variability in your measurements also varies quite a bit. So we have these oscillations in our expected variability. Well, we don't want that in calculations for patients, because if you're only, so this might be 3 days or 4 days, and then when you're 7 days, it's quite a bit different, these from here to here. So what we were then able to conclude and give and advise clinicians that in order for you to discount the effects of natural variability in a patient, you need to separate your measurements by at least 40 days, because then you can account for this variability, subtract it out, and if you still have an increase, then maybe the drug therapy the patient's on is not working. So that was a very interesting result, and we are very excited about it. And we were also able to put on other clinical studies onto this figure, and we were also able to see that these clinical studies, so this was 1 day apart, is very close to what we would measure. Here is 3 weeks apart, the measurements, and it's also very close to our model. So that again told us that we need to model 10 to 15 microliters of blood in order for us to replicate what's happening in the clinics. Okay, so that was something that we can look at for HIV. Now let's move on to some different infections. Specifically, we're going to look at measles and pertussis. So this is a diagram of all of the outbreaks of measles and whooping cough, or pertussis, in the world from 2008 to 2015. And you can see that there are certain areas of the world that are plagued by measles still. Same with here, they're quite large outbreaks. And you can see that over here in populations where we have a nice high level of uptake of pertussis vaccine, we're having these small outbreaks of pertussis in our communities. And you probably heard recently about measles and pertussis outbreaks, even within the GTA. Okay. Well, now looking at an acute infection, we want to develop models where we have some development of immunity after you clear the infection from the body. So you can think that here's an acute infection like measles or pertussis, where you have entry of the microorganism, then you have some increase of the pathogen in the body, and here's when the adaptive immune response starts to really work and kill those infected cells and get rid of all those virions by antibody. And then you can see that that's when you get the decrease, you get pathogen clearance, and then some of those activated cells then become memory cells. And those are what we call your immunity. So you can have B memory cells, CD8 T cell memory cells, and CD4 T cell memory cells. And those are what your immunity is composed of. Why is that important? Well, that means that if you come into contact with the pathogen again, just weeks later, then you'll get an immune response, but you won't be infected. And then if you come into contact with the pathogen again years later, then you may get a mild or inapparent reinfection. Hopefully you still have a robust level of immunity that's good enough still to decrease your probability of transmission or symptoms or the severe side effects of having the disease. But this immunity could wane, and that may be why you could get an inapparent reinfection, or you might just get a reinfection that's mild and you can have some symptoms. Okay. Well, we can develop in-host models for acute infections as well, where we can really try to determine, okay, if I have an individual that's exposed to infectious disease at age 1, say these are childhood infections. You can think that they have a brother or sister that went to school, got infected, and then they brought the disease home. Okay? You can think that, okay, around age 1, they can be infected, so here's our virus here, and they get this boost in their immunity from 0 to this quite high level here. So here's our memory. These are our memory cells. Okay. Then the immunity may wane over time, suppose, And then they start elementary school at age 5, and they become exposed again, but they don't actually get an infection. They just get a boost in immunity. And then say we're looking at something that comes in to the population every other year, then you could think that maybe they're exposed every other year while they're in elementary school. And then when they graduate elementary school, go off to high school and become an adult, they're not exposed again. So they've changed the people they hang out with. They don't hang out with those little kids anymore. Then their immunity can wane quite a bit, so that now when they're an adult and they have a child that has gone off to school and brought the infection home, they may actually experience an infection that's subclinical, and this is actually using our mathematical model defined as a subclinical infection where they won't show symptoms or a very mild level of symptoms, but they'll have transmissibility. The transmissibility will be significantly lower than if they had no immunity at the time that they were infected at all. And so then you can think that maybe their next child goes off to school and so on. So these are things that we can look at with our mathematical models, trying to define development of immunity mathematically, and then trying to use that to tell us how do we define immunity in terms of susceptibility and transmissibility at the population level. So we can take information from our in-host models and now embed them into epidemiological level models where we're susceptible. I'm going to ignore that exposed compartment now. Just go susceptible to infectious to recovered, and then a waning immunity compartment. And now I'm talking specifically about pertussis, or whooping cough. We know that pertussis is affecting populations that have a high level of vaccine uptake. Okay, we have these small outbreaks. What do we know about pertussis? Well, we know you gain immunity after vaccination or natural infection. We also know that immunity does wane for this disease. And we know that after vaccination, it can wane between 4 to 12 years, and for natural infection, 4 to 20 years. Okay. So if we incorporate all that information, we also know how long it takes for you to recover when you're infected with pertussis. That's a pretty well-known number because we've studied pertussis for a long time. And using the prevalence of infection in the population, we can then use that data to determine what the transmission rate is on average between different age groups in the population as well. Okay, so what we did with this 4-compartment model was develop a system where now what we're going to do is we're going to change the birth rate and the life expectancy of our population. So you can think that over the generations in a population, the birth rate has changed significantly. I don't know about your history, but I'm from Irish Catholic farming family, and our birth rate has changed drastically. Okay. So, and we also know that with the advances in medicine, our life expectancy is going up. Okay. So what happens if we just change our birth rate and our life expectancy in this model? Life expectancy has to do with your natural death rate. Then what if we modify the rate of waning immunity? So we know that it's different if you have natural infection versus vaccination. So what if we modify that rate? And we know that different vaccines give you a different level of immunity as well. So there's a different waning rate for those vaccines too. What if you modify the boosting terms? That means if you become exposed to the disease again, do you get a big boost or a small boost in your immunity? And so that has to do with your susceptibles going to the infectious compartment. And what if you, oh no, that goes from the W to the R compartment. And then what if you change the intensity of infection? So you can think of seasonal forcing. We know that there are certain seasons in the year where infectious diseases are more prevalent. Okay. And so what if we change the intensity of how individuals interact during those seasons? And how is that going to affect the susceptible population going to infectious and so on? Okay. Well, we used this model to look at many different life expectancies for similar parameter values for all of these other things, intensity of infection, boosting of immunity, and so on. Okay, so here are a lot of figures that we drew for this model. What's the most important for you to take from this figure here is this green area is getting bigger. What do all these colors mean? Well, these are different periods of infection that you can expect this is a deterministic model, so no probability. Okay, so these are different periods of infection that you can expect in a population given certain parameter values that we use to generate all of these graphs. Okay, now the only thing that's changing is our life expectancy, which also changes our birth rate because we're assuming a constant population size. You can see what's happening is this green area is getting larger, and it's going towards the left. Okay. What is that green area? Well, let's first look at these two parameters. Here we have your immune boosting, so your strength of immune boosting, and here we have your intensity of infection. And if we change your life expectancy from 50 years to 75 years to 100 years, this green area moves to lower intensities of infection, which is similar to a highly vaccinated population. Okay? And you can also think that, well, it's kind of constant around many different levels of immune boosting. This green area represents something that we call a period 3 in mathematical modeling. And what a period 3 means is that, well, after you have a period 3, the next step is chaos. So if you get out of a period 3 region, you can then have an infectious disease in your population chaotically. What does that mean? Well, it means that you can't control it very well because you don't know what to expect. So then you have to control your chaotic dynamics down to something that's in a nice period again. So now you know what to expect, and then you can bring in new public health controls to try to bring that down so that you can effectively get rid of the disease in the population. So looking at this in more detail, we found that as we vary the duration of immunity, and so here we went from 1 to 20 or so years, we can get very large changes in our period of oscillation. So you can actually go from a period of oscillation of close to 1 to about 2, and very drastically, just from one number to the next. And same with here, you can get this big change as well. So these are indicative of something called a crisis in population biology infectious disease modeling. So what if we take the parameter values at one of these crises and plot our periods that we would expect? So here we're just plotting a period 5 and a period 3, and then this red line here that's going around the period 5 is chaos. So this says that if we're in a parameter regime where we expect a period 5, so it's like 5 peaks that keep on repeating over and over again over so many years that we can also measure, that I haven't shown you here. But if we perturb the system just slightly, maybe with a new vaccine, or maybe there's some vaccine hesitancy in the population so that we decrease the level of vaccine uptake, that we could go into a chaotic regime. And that's not great. So we would need to then further understand how to control the chaos to bring it down to something that's periodic again, so that we can figure out what to do to get rid of the disease in the population. So we can also do a very similar thing for measles. And this is a hypothetical question. So many people believe that once you're infected or you get the vaccine for measles, you have lifelong immunity. But like I said before, what if your lifelong immunity is really just an effective immunity, where you just keep on getting boosted periodically throughout your life because you've become exposed again? And so your immunity is really just being boosted over your life, and so effectively it's lifelong. Well, we can develop an in-host model again that will allow us to use just looking at areas underneath all of these curves to determine how long you are in this exposed class or the infectious class, depending on what level of immunity you had at the time of infection. Then we can relate that to your transmissibility at the population level. We can also say if you had a certain level I of immunity at the time of infection, then now after you've recovered, you have a level P, and that's what this figure is here. So now we can incorporate all this information from the in-host model into a population level model that's SEIRS, so waning back to susceptible. Well, what can we see? Well, hypothetically, if immunity to measles wanes over time, then we can also get periodic outbreaks, similar to the pertussis scenario. And what happens, so when do we get these periodic outbreaks? We find that for a high vaccination level, greater than 70% uptake, and moderate waning immunity, so about 30 years, you can get large-scale epidemic cycles. And this figure here plots a 92% vaccine uptake, and these are waning rates where your immunity wanes over 30, 40, 50, or 60 years after natural infection. So you can think that effectively, if your immunity is waning over 60 years after you've been infected, then you really do have lifelong immunity. And so what we thought was really interesting about this is that when we look at our exposed and infectious individuals in the population, and this is our susceptible population, when we look at these, well, using the in-host model, we were able to determine definitions of asymptomatic infection. And when we included that definition into here, we actually saw that a very large proportion of our exposed and infectious individuals in the population are going to be asymptomatic, but still be transmissible. And so large populations could actually harbor measles asymptomatically. But there's a warning here that to look at this, we used a deterministic system of ordinary differential equations. What does that mean? We assumed that you are all in a population and there's someone stirring you. So stirring you around the population so that you had an equal probability of meeting anybody in the population as you would your brother or sister. Okay. So this is something that we looked at that was really interesting. The result also gives us small outbreaks of measles every 10 to 15 years, which is what we see in populations that have a high vaccination uptake. But the model is not a great reflection of reality and how people interact, and so we need to do more studies involving that biological detail. Okay. Finally, I'm going to touch a little bit on flu. So here, what we can consider two kinds of flu. There's pandemic flu, which occurs once in a while. What we know about pandemic flu is that when we have a pandemic, we have multiple waves of infection. So here is a flu this is London, that went through London in 1889 to 1892. Here's the 1918, 1919, and this is Copenhagen. Here's 1957 to 1963 in the United States. And here is 1968 to 1970 in England and Wales. So when you have a pandemic, you will get multiple waves. And we saw that with the 2009 H1N1 pandemic as well. We had a wave, and then over the summer, it reduced quite a bit. And then in the fall, we had a second wave. And we were expecting that wave again. And so we were really trying to get the vaccine out in time so that people could get the vaccine so that they'd have protection before the second wave started. Well, what do we know about seasonal flu? Well, seasonal flu happens every year. We have a flu season in certain populations or certain countries in the world that are more in the northern and southern points of the globe. And in the middle, it's kind of a more constant level. You could have flu any time of the year. But we have a flu season in Canada. And what we know is that mainly right now, seasonal flu is caused by a strain called H3N2. There's also a seasonal H1N1 strain. And we also are going to consider that pandemic H1N1 strain because that could have, once a pandemic strain comes into the population, then it can overtake one of the seasonal strains and become the seasonal strain itself. Okay. What we're interested in knowing is, okay, for seasonal flu, can we actually get a better prediction of what the strain is going to be that's going to cause our next flu season? Okay, so what happens now is that we look at what strains are predominant in the southern hemisphere, and we make a prediction, figuring out what strains are predominant there. We make a prediction to what's going to happen in the northern hemisphere, and we make the vaccine against those strains that we've predicted. Why do we have a 6-month difference? Well, we need that length of time to grow our vaccine. Okay. What if we use a mathematical model to study the evolution of seasonal flu over time? Then we might be able to get a better idea of what the flu strain is going to be in our flu season, so that we can have the length of time we need to grow our vaccine in eggs, or even there's some new technologies where they can grow the vaccine in a couple of weeks. Okay, so I'm going to skip this and go right directly to that seasonal flu study. So what we have are data of all of the H3N2 strains that are reported in seasonal flu from, I think we went back to like 1980 something, and here I'm just showing you 1998 to 2012. And so what we did is we took all of that data, we have the amino acid sequences, we were able to group them into families. And this is, the methodology was developed by my collaborator, Stephen Wong at York, and this is also in collaboration with Hannah Jankowski at York University as well. So we were able to group all of those strains into families. Then what we did is we took all the vaccine strains that we had over the years. So we had a 1999 strain, Moscow 1099, that's just the name. And we used that as our vaccine until 2002, when we changed it to this. And then we used that vaccine until 2007, until 2004, when we changed it to this, and so on. Then what we did is we put those vaccine strains into our analysis as well to determine what families they reside in. Then we looked at the dynamics of evolution over time. And so here we're showing our clusters, so all of those clusters here, so we have 23 clusters. And so here we have all of our 23 clusters, and you can see that over time some increase and decrease. Now the magnitude could be just a reporting bias, because more strains could be reported over different years. Okay? But you can see that when one is dying out, another one is on the rise. And same with here. And so what we see is that every 3 to 4 years, the dominant family of strains can change. So then what we did is we looked at all of our vaccines. And so here in 2000, 2001, our families or clusters 1, 3, 4, and 5 existed. And our vaccine was in cluster 2, and our dominant cluster was cluster 1. So you can see that our vaccine was in a different cluster to the dominant strain that was causing the flu that year. And same with here, so cluster 2, and you can see that the seasonal flu is evolving and moving from one family to another family, so 1, 4, 6, 6, and so on. Then you can see in 2002, we changed our vaccine and now it resides in cluster 6, and that was right after a year where a strain in family number 6 was dominant. So we changed our vaccine, and our dominant strain moved to cluster 9. Now that could happen just naturally, or could have some sort of force because of how closely related our vaccine was. Then we changed our vaccine again, and now it's in cluster 9. And we still had a dominant strain in 9. We kept our vaccine in 9, and our dominant strain moved to 11, and so on. And you can see that really, so you can see your dominant strains are moving up in cluster number, and our vaccine has these steps, and it's trying to catch up. Okay, so now if we know all of this information from the past, maybe we'll be able to now make predictive models of what strains are going to be important from season to season, knowing what's happening now in the southern hemisphere, for example, or in the northern hemisphere. Finally, I did say I was going to touch one slide on social distancing. And what this really is okay, during the last pandemic, when you heard all of those announcements on the radio, or you can even think during SARS, you heard all those announcements. Something that you did was you tried to limit your contacts. So you're reducing the probability that you would be exposed to the pathogen, thus reducing the probability that you would be infected. Okay. Well, you can, as you practice social distancing, then you could say that you move from susceptible to S1. So that's some level of social distancing. And then up to S2 is another level of social distancing, and so on. There could be many different levels. Well, what's important about this, and you've seen that I'm interested in looking at waning immunity, I'm also interested in looking at waning behavior. Because just naturally, even after you decide to practice social distancing to a certain extent, over time, your behavior will just naturally wane, especially if you don't hear about the pathogen or the disease a lot in the media. Or it can also, though, the more and more you hear about it, you can become desensitized to it as well, and your behavior will just wane. So what we did is we took a pandemic H1N1 model, and what we did is we incorporated the mass media reports globally in English and French into our system. So now we have mass media reports that are helping move people from S0 to S1 to S2, but then you just naturally wane back as well. What we found is that if your behavior wanes, you can have a first peak of infection, and this is when you think, okay, now we have this like constant level of media reports, so people aren't having these big differences in exposure to the media, and it's not scaring them with respect to the disease, for example. Their behavior can wane, and what that means is that now your behavior has waned so much that now you're replenishing these number of susceptibles that the disease can have contact with, and you can get a second wave of infection. What's really interesting about that model is that, okay, we now have a multiple wave, 2 waves of a pandemic that just has to do with population behavior. We also included the vaccine for the second wave, but it had nothing to do with antiviral treatment or the development of resistance or things like that. And so now we're thinking that if we involve all these other things, we can really get an idea of how effective a media campaign is in informing the public. And we want to know what's the optimal level of a media campaign so that you're not being bombarded by the information so that you don't care anymore, but you're getting enough information so that you're sure to keep those positive social distancing practices at hand. Okay, so here is a process of modeling that you can think that I'd be considering for all of my projects, and especially in close collaboration with collaborators, stakeholders, and policymakers. And this is really where I reside in this circle. So I use statistical computer models and mathematical models and refine them and do a sensitivity analysis. Now, I talked about a lot of different results in this talk, but I really want to give you a warning is that none of what I actually told you is the truth. Okay? That it's something that could happen, but like I said, I have so many assumptions in my models. I'm really trying to get to that peak where I have a simple enough model so I get robust results, but it's still kind of hard to tell where I really am on that graph. So what we try to do is compare to data and talk to people in public health and really try to gain more knowledge that we can put into our models so that we have less uncertainty. I also, though, showed you a lot of deterministic results. We know that the world is probabilistic. So there's some stochasticity. There are fluctuations that in all of our measurements that we really should be taking into consideration. I talked a little bit about social behavior, but I didn't model decision making. That's game theory we could incorporate into our models. I didn't really talk to you about mutation and evolution of drug resistance or the evolution of the flu in a dynamical model. We were just looking at the statistics and trying to figure out the families that these things look at. Seasonal forcing, that's something that's also important. During different times of the year, we have a better environment and more contacts that are optimal for different pathogens to be transmitted. And so on. There's just so many other things that we need to include. And also, I talked a lot about population health. You also need to consider individual versus population health, and that's something that we're really trying to look at in that multi-scale problem. Okay, so here are the collaborators that helped me with all of this work that I presented today. I'd really like to thank the RCI for Advancement in Science and the CDM, without which I wouldn't have been able to really do a lot of this work. And I've been funded by MyTax, the Government of Ontario, and CERC, the Public Health Agency, and CIHR. And what I just want to leave off with is, so what a lot of people say is that they're really trying to fit the puzzle pieces together. Well, when you're looking at problems like what I'm looking at, which are multi-scale, you really think that the puzzle pieces don't fit together, they overlap. And so what you're really is you're just stacking puzzle pieces on top of each other, which then you think that when you're looking down on them, hopefully they make a nice, pretty picture that's realistic. Thank you very much.